Now we will start the matching using the LC sections. Now earlier what is there, we had a transmission line where the load is connected. Similarly in that case also we can have a transmission line section who is having a characteristic impedance Z0 and propagation constant beta to which a load is connected. In earlier case we used to connect the sections of transmission line either series or parallel to realize the impedance matching for Zin is equal to Z0, and one of the drawback for that was you are actually required to move down the length of the transmission line, identify the location of that particular L1 where you are going to put that respective length parallel or series term. Now, so the matching was not really realized at the point where the load was connected. In this case, we will be realizing the matching at the point where the load is connected. So at the load point itself, by doing some modifications in the discrete form, we will be realizing Zin is equal to Z0. So over the entire length of the transmission line, we will have the impedance matching. So what we are doing, we are going to insert the LC elements. Remember again, LC elements are insert, no R is inserted. So we are not changing the loss factor, the gamma factor which is there in the transmission line. So LC elements will be entered, and then at this point itself, we will get Zin is equal to Z0. Now two cases are there. This particular methodology differs with respect to where the impedance is located. The approach you are going to take for LC matching differs if the impedance point or ZL is lying outside R1 circle or if the point is lying inside R1 circle. So I have taken two cases. One is the point which is lying outside R1 circle and another one is the point which is lying inside R1 circle. Now remember, very important factor over here, we are going to use a Z Smith chart and we are going to use a series parallel combination. So we are going to use Z as well as a Y Smith chart also, because LC element will be introduced not just in series but as well as in parallel. Very importantly, we are going to avoid the LCL section, that is the inductor section coming in parallel. Because what happens is in microstrip realization of the LC element, realizing a parallel inductor is a difficulty using the microstrip sections, which capacitors can be realized. Hence, we are going to avoid parallel elements or parallel inductors precisely. Now let's do the impedance matching of LC section for the point which is lying outside R1 circle. So the point is mentioned over there. It is 0.4 plus j 0.3. This is the impedance point which is there. So I have located the impedance point over here. So this is my impedance point. What I need to do? I need to go over here. So through some means, through some addition of LC component, I need to go to the center. Now, if I add any series or parallel inductor to this, I am not at all going to reach to R1 point, that is the center point, because my goal is to reach that point. So if I add any inductor in series or capacitor in series, I am just going to move along respective R circle. I am not going to touch in the center. Even if I add any parallel, that is not going to happen because it will move around corresponding G circle. Okay, so that is also not possible. So in this case, what we need to do always in this LC matching case, along with this constant R1 circle, draw constant G1 circle on the Smith chart. Okay, constant G1 circle. Why? Because as I told you earlier, we are going to use Z as well as Y, Z Smith chart as well as Y Smith chart also. So from that perspective, we are going to draw G1 circle along with R1 circle. Now what G1 circle is? Conductance 1 circle, which is there in the corresponding Y Smith chart. So for that, what you do, you take the diameter distance of R1 circle, find out the radius of this, and then mark a center over here. And then with respect to that center, draw this R1 circle. So in that process, you are going to draw two tangential circles which are meeting at the center. This is G1 circle, that is conductance 1 circle. Okay, which is drawn for the simplicity purpose on the Z Smith chart. Okay, so this is the first step what we are going to do. Now, after that, what you need to do, from this point, you try to go approach towards G1 circle, because you cannot approach R1 circle, but through some addition of inductor or capacitor, I can approach G1 circle. But in that process, I am not changing the value of R. Remember, resistance are not added, only L or C are added. So if I add inductor over here, then it moves up along constant R circle. If I add a capacitor in series, it moves down along constant R circle. So how much capacitor or how much inductor to be added? Now let's take the first case. We will add an inductor in series. So here to this impedance, I will add an inductor in series. Okay. So how much inductors to be added? That value depends upon ultimately where is my destination. Where is my destination? I should reach this point. I should reach G1 circle. So I should be adding that much inductor. So what you should do, your path should be like this. You are going to start from the point where 0.4 plus 0.3J is there, and you add a value of inductor delta L such that you arrive over here. So what is the final inductor which our final impedance expected over here? It is 0.48J over here, because this point I am talking, it is 0.48J. So how much inductor I am adding? It is basically 0.48 minus 0.3 J is equal to J omega L by Z naught. Remember, it's a normalized value. So that is the value of the inductor which I am going to add in series, so that I will move up along constant R circle and reach G1 circle. So this is the point where I have reached. Okay, so I have added inductor in series. If I add a capacitor in series, what will happen? It will come down. How to calculate that value? Ultimately, I have to reach here. So just mark a point over here and see what is the destination imaginary part value is. So it is minus 0.5J. So minus 0.5J minus 0.3 is equal to 1 upon J omega C Z naught. In other case, it will be minus 0.5J minus 0.3 J is equal to 1 upon J omega C Z naught, because it is a capacitive impedance. Okay, it is a capacitive value, so that's why it is equal to this. So if I add a series capacitor over here, I am going to have a value which is added like this. So note, you should be calculating the value like this. What is the destination value? Destination imaginary part minus the initial. That difference should be equated to either J omega L by Z naught if it is plus, or it is should be equated to 1 upon J omega C Z naught if it is a negative. Means what? Negative impedance. That is basically offered by your capacitor. So initially I am not considering the capacitor part first. Why? I will tell you later. Okay. So here I have added an inductor. I have reached to G1 circle. So I have added an inductor. The value is calculated at a given frequency using that equation. Okay. After that is done, you have reached G1 circle. Now I do not have JB arcs. Okay, I do not have JB arcs, so directly I cannot go down, because although I am using J1 circle, G1 circle I have drawn, but I do not have the JB arcs. I am not using ZY Smith chart. So directly in one shot I cannot go back to the center point. Okay, while moving along constant G circle. So what I will do, I will take a diametrically opposite point from this point to the R1 circle. Remember, any diametrically opposite point lying on G1 circle will always arrive on the constant R1 circle. You can take any such combination, you can verify yourself. So diametrically opposite point from G1 circle will arrive at R1 circle. So you take the diametrically opposite point. So what you have done, you have actually, this is Z which is over here after adding the inductor, you have come to the corresponding Y of that. You have come to the corresponding Y of that. Okay, so now you are on the admittance domain. You are on the admittance domain. So any now changes you are going to do to the circuit now will be done in parallel. Now will be done in parallel. So what you have done, earlier you have added a series inductor. Now you are over here, but now you are considering Y. So whatever you are going to do on the circuit level now will be done in the shunt or the parallel case. Okay, so you are already on R1 circle. What is the admittance over here now? 1 minus, you just see the value, 1 minus J1.3. 1 minus J1.3, it is the value of the susceptors. 1 minus 1.3, or admittance is 1 minus 1.3 J. What you need to do? You need to go to the center. What you need to do? You need to go to the center. So what you need to add? You need to add susceptance of 1.3 J. You need to add a susceptance of 1.3 J. Now, susceptance of 1.3 J is basically susceptance I am talking, that equals this value, that is capacitor in parallel. Okay, susceptance positive means capacitor, susceptance negative means inductor. That one should know. So positive susceptance you need to add. So I need to add a parallel capacitor over here. So if I add that, naturally my Y will be equal to 1 or Z will be equal to 1. I am realizing the impedance match. So the value of the capacitor will be found out like this. Once you take a diametrically opposite point, read the value of corresponding JB part, and that JB part, negative value of that needs to be equated to the respective capacitor value, and then that value will be calculated from that equation which is mentioned for the given frequency. So what you are doing, earlier you had a series inductor, the value is calculated using this equation, and then you had a parallel capacitor, the value of that is calculated using this equation, and in the process you have arrived at the center point. In the process you have arrived at the center point. Okay, if I would have taken the other route, I would have come down in the previous case, I would have added series capacitor, fine. But then if you have taken a diametrically opposite point and come on R1 circle, where I am back onto the admittance domain, I am taking the other route, other explanation. So here what will be there? The admittance over here will be 1 plus something, 1 plus JB. So what you need to do? You need to add minus 1 plus JB, minus JB over there to negate that and make Y equal to 1. So minus JB susceptance equals minus J Z naught upon omega L. That is the parallel inductor. So parallel inductor, as I mentioned right in the beginning, are not allowed. Hence, we are not going to take the other route. We are going to take the upper route where you have added an inductor first and then the capacitor. Okay, just to give you few more examples, suppose the point is located somewhere here. What you will do? You move along constant R circle. Of course, draw R1 circle first. You move along constant R circle. You will touch this point and this point. Which point to go for? Naturally, the top one. In both the process, you are going to add a series inductor. Okay, in both the processes, you are going to add a series inductor. But if you go over here, this step will lead to a parallel inductor. So that is not acceptable. So if the point is over here, move along respective constant R circle till you intersect G circle on the top. So you have added a series inductor. How to calculate that inductor value? Destination J minus source J is equal to J omega L by Z naught. And then you take a diametrically opposite point over here. So you are on admittance domain. You have a one minus JB as a admittance. So you need to add a susceptance of 1 plus JB, which is a parallel capacitor. So that is acceptable. So here always take the first step, that is going towards the top part of the G1 circle. If the impedance is over here, because see there can be so many cases. If the impedance is over here, what will happen? Always move along constant R circle and reach over here. Okay, you can reach down also, but as I said down, the next step will lead to a parallel inductor. So reach over here. In this case, you are going to add a series capacitor. Okay, you are going to add a series capacitor, and then take a diametrically opposite point will come here. Then you are going to add a parallel capacitor. So if the point is over here, both the capacitors will be there. If the point is over here, inductor and capacitor will be there. So that way the selection of the elements in the LC section matching will change. Okay, so this is all about the point which is lying inside outside a R1 circle. Now let's see the point, what will happen if the point is lying inside R1 circle. So I have located a point over here. Okay, I have located a point over here. This is my impedance location. Okay, 1.8 minus 0.2 J is my impedance location. So I have located a point over here. What is my ultimate goal? I have to reach the center. What is my ultimate goal? I have to reach the center. Can I go directly? No. If I add series inductor or parallel inductor, Will I reach R1 center point? Not possible. It will move along respective constant R circle. Again, no changes in the value of R. So direct path is not acceptable because you are adding a loss component. Okay, so that going from here to the center is not possible. Even if I go to the admittance side of it, then also that is not possible. If I try to approach G1 circle, that is also directly not possible. Okay, so what you will do here now, in this case, what you will do, you will draw a constant gamma circle. You will draw a constant gamma circle over here. Okay, why I am doing constant gamma circle? Naturally, we want to go to the admittance side. But admittance side, after going to admittance side, as I mentioned earlier, after on Y domain also or Z domain, I am not able to reach R1 circle. I will try to reach G1 circle through that process. I will try to reach G1 circle to that process. So here, I draw it more precisely. So this is my constant gamma circle for that point. Then I will take a diametrically opposite point so that I come on the admittance domain. I come on the admittance domain. Okay. So my point is this now. Okay. But where I am now? I am now on susceptible Y plot. I am treating now my Z Smith chart as a Y Smith chart. All my R curves will be treated as a G curves. All my arcs, J plus arc minus J arcs, will be treated as the JB curves. Okay, so I am over there now. What I will do, once I have gone on to the admittance side, I will try to approach G1 circle. Okay, also I will try to approach G1 circle and I will try to add positive susceptance. Remember, I am going to add positive susceptance because positive susceptance will lead to a parallel capacitor. Okay, so what I will do now, I will after taking out a diametrically opposite point, finding Y of that particular Z, forget about constant gamma circle now. That was just for the transformation. Now what I will do, I will locate the corresponding R circle where it resides upon. I will locate now corresponding R circle. So you find out which R circle onto which this point is lying. Because any moment henceforth will be done on that constant R G circle. Okay, now that R circle is treated as a G circle. Okay, and then from that G circle and after identification, try to move up till you reach G1 circle. Till you reach G1 circle. So what you have added? You have added a positive imaginary component or positive susceptance. Okay, how you calculate that value? Something similar to the previous one. Destination imaginary part minus the source imaginary part, but now it is equal to j omega c z naught. That difference is now equal to j omega c z naught because we are working on admittance domain. We are using Z Smith chart as a Y Smith chart. We are working on admittance domain. So we are over here. So we have added initially now a parallel. So this was our load impedance. Now we have added a parallel capacitor. Now we have added a parallel capacitor. After that, what is the next step? Naturally, we do not have those JB curves. So we cannot directly come down from G1 circle to the center point. So we have to go back onto the impedance domain. We have to go back to the impedance domain from this. So draw a diametrically opposite point from G1 circle. Draw a diametrically opposite point from G1 circle, which will bring you to R1 circle. Which will bring you to R1 circle. So you are back on impedance Smith chart. You are back on impedance Smith chart. Okay. So you are now on Z domain. So what you will do now? Sorry, I have done a mistake over here. Actually, the point I have taken was something wrong. Just a second. Diametrically opposite point. Okay. So this is my diametrically opposite point. It is over here. Okay. That was for the previous example. Okay. So the diametrically opposite point is somewhere here. Right. So this is my point now. Again, I am back on impedance domain. So you read the value of impedance over there. You read the value of impedance over there. Naturally, it will be 1 minus 0.85J. That value will be problem specific. It will be 1 minus 0.85J. So this point impedance will be 1 minus 0.85J. Okay, so what you need to do? You need to add plus 0.85J now in series. Why? Because you are on the impedance domain. So you add plus 0.85J in series, which is equal to J omega L by Z naught, which is equal to 0.85J in series is equal to J omega L by Z naught. So you are going to have a series inductor as the next element. You are going to have a series inductor as the next element for the impedance matching. Okay, so in case of point lying inside R1 circle, remember first element will always be parallel capacitor. Okay, always will be a parallel element, and naturally we are selecting a parallel capacitor, and later on it will be a series inductor. Okay, so this is the impedance matching case. Now you can take any arbitrary point. Suppose the point is lying over here. What you will do? You will take a diametrically opposite point and come over here. Naturally, locate that corresponding R circle onto which that point is residing, and then add a positive susceptance to it so that you will reach G1 circle. So you have added a parallel capacitor. After that, take a diametrically opposite point, come back on impedance domain. Come back on impedance domain. So you are now doing any modifications in series, and naturally after that you are going to add a positive impedance. That means you are going to add a positive impedance, that is a series capacitor, series inductor. So the circuit more or less remains the same. Okay, parallel element always will be the first, and that is going to be the capacitor. Later on it is going to be the series inductor for the impedance LC matching networks when the point is lying inside R1 circle. So this is all about impedance matching using LC sections. Okay, advantage of that, we are immediately putting it right in at the load point rather at a distance away from the load point. Remember, these values have to be calculated, and once that network is identified, always for that given frequency find out the respective impedance, and then through the mathematical calculations prove that Zin is equal to Z0. This calculation have to be shown mathematically to prove that your LC section matching is working. Even in the case of transmission line also, you need to calculate the sections or other impedance or other length of the transmission line using those formulas of ZOC, ZSC or YSC or YOC, and then prove that length what you obtain using Smith chart matches using the calculation. So here we end upon your impedance matching network. In the next topic, now we will start with the dpi network. Thank you.